It is well known that the oceans provide most of the heat and water vapor that is required to maintain the huge weather systems of the Earth. But it is not so well known that the oceans can also play a role in the formation of rain by supplying sea salt and electric charge to the atmosphere. Here, seen through the microscope, are crystals of sea salt. Crystals like these have been found in the upper atmosphere where clouds form. In clouds, they act as giant condensation nuclei around which raindrops can form. We believe that the presence of electric charge is important in this process. But let's start at the beginning. How do sea salt particles get into the atmosphere? To answer this question, we have been studying the bubbles of air that are formed at the surface of the sea by breaking waves, the bubbles that make the foam you see. These air bubbles are quite small. To examine them carefully under controlled conditions, let's go to the lab. It's a simple matter to produce bubbles in the laboratory, and we're doing it here because it makes it much easier to study them. We have a tank of seawater, some plastic hose through which the air is being forced. It comes down this way and up through a porous ceramic filter. I think you can see the filter much more clearly if I stop the air supply for a few seconds. Now look closely in the air, just above the region where the bubbles are breaking. Notice the fog of tiny droplets produced as the bubbles break. These air bubbles come from a compressed air line. How are bubbles made in the sea? With this beaker of seawater, I'm going to simulate the production of bubbles by breaking waves. Now watch closely what happens when I pour this seawater into the container. There, I think you can see the bubbles which are being produced. And just above the seawater, you can see the fog of droplets. But now look, we don't have to have as much water as that. We can allow just single drops of water to fall into seawater, and you get bubbles produced. So the splashing of water into water and the bubbling of air through a porous filter provide a reasonable simulation of what happens on the open sea when waves break and bubbles are produced. In fact, we have made measurements of the concentration of bubbles just after a wave is broken, and we have found upwards of 100 bubbles per cc of seawater. I would estimate that you are seeing about the same bubble concentration here. But how do bubbles breaking at the surface make drops in the air above the water? Let's change our setup so that we can look at individual bubbles. Here under the water is a fine hair-like tip drawn from a piece of glass tubing. Several bubbles per second are being formed. These streaks of light we see in the air are droplets formed by the bursting of the bubbles. We have droplets in the air and bubbles breaking on the surface of the water. But we can't really see what happens when the bubbles break. It occurs too rapidly. But we can make slow-motion movies to look at this process. What you are seeing now has been slowed down by nearly 200 times. Let's look at that again. As the bubble cavity collapses, A pencil-like jet of water rises from the bottom of the cavity. This jet becomes unstable and breaks into drops which continue upward. We call these the jet drops. These drops are ejected at very high speeds. But what do these jet drops really have to do with sea salt particles in the air? To answer that question, we're going to have to catch some of these jet drops from the bursting bubbles and examine them under the microscope. And to do that, I'm going to use this wire frame. Around this wire frame, I have a number of spider webs. We can pass the frame and the webs slowly through the fog of jet drops, and in so doing, we capture some. This chamber is used to control the moisture in the air around the jet drops. At the present time, this tubing carries moist air into the chamber. The air is coming from this humidifier. We also have a chamber to dry the air, which we'll use later. Here, caught in the web fibers, we have the jet drops. What do you suppose happens to them over the sea as they are caught up by the wind and carried up into drier air? We can simulate that process by switching over so that dry air will now enter our chamber. The water evaporates and leaves behind sea salt particles. Particles of sea salt just like these have been collected in the air over many parts of the world. Here are some as seen through the microscope that were collected by Dr. Alfred Woodcock of the University of Hawaii. These sea salt particles are the giant condensation nuclei. Let me show you how we think these sea salt particles play a role in the formation of raindrops. If we pass moist air into the chamber again, the sea salt particles absorb moisture and begin to grow. The same thing will happen in a cloud. But in a cloud, they also will begin to fall amongst the smaller cloud drops. Like a rolling snowball, they sweep up the small drops in their path, grow even larger, and emerge from the cloud as raindrops. Now, we believe the rate at which this happens can also be influenced by electric charges in the air or on the drops. I mentioned earlier that electrical effects in the atmosphere most probably play a role in the initiation of rain. And I'd like to demonstrate one of these effects to you now. And then, after that, we can see if the oceans produce any electrical effects of their own. This piece of equipment is relatively simple. It consists of nothing more than a piece of rubber hose coming from the faucet and leading up to this piece of glass tubing. The tip at the end of the tubing has been drawn to a diameter of about 1 millimeter. This is called a Rayleigh fountain. It's named after Lord Rayleigh, who studied this nearly 90 years ago. This is slowed down by about 5 times. Notice how it's behaving now. The droplets are forming at about this point. They are going upward, they bounce off each other, and as a consequence, they spray out in all directions at the top of the fountain. Now watch what happens. When I take my comb, run it through my hair to charge it electrically, and hold it near the fountain. The droplets no longer bounce out at the top of the fountain. The droplets are coalescing. In fact, they often form this one big drop which falls downward. If I take my comb away, the fountain behaves as before. You can see how the electric charges on this cone are able to influence the growth of droplets. This simple experiment demonstrates how electric fields in the atmosphere can alter the electrical characteristics of water drops so that they merge much more easily. We believe that this sort of effect can play a role in the formation of rain, and there are other electrical effects we think may also be influential. Now, you've probably noticed that up to this time I have used words like perhaps, I think, or maybe. The reason I do this is because those of us who are working in atmospheric electricity don't really understand just how important the electrical effects are in the production of rain. We have many ideas and many theories, but there is also much disagreement. In any event, to have any electrical effects at all, whether it is lightning or otherwise, it must begin with the production of charged particles, either in the atmosphere or at the surface of the Earth. Now, at the present time, most workers believe that the positive charge of the atmosphere, which is well known, originates from thunderstorms. But it may be that the oceans are playing a role also. Over here is an experiment that will show us if the jet drops carry an electric charge. I have a tube of seawater within which a glass tip is producing individual bubbles. The bubbles are breaking at the surface, and the jet drops are rising up between these two plates made of wire screening. Now, if you look closely, I think you can see that the drops are going vertically upward and falling back pretty much along the same line. I have, in addition, a high voltage DC power supply. I'm going to connect this right-hand plate to the positive side of the power supply and the left-hand plate to the negative side of the power supply. And now, when I turn the power supply on, we are going to have negative charge in the left plate and positive charge on the right plate. Now, let's see what happens. The drop is repelled by the right positively charged plate and attracted to the left negatively charged plate. Now I'll reverse the leads so that the negative charge is on the right plate. Now the drops are being attracted to the right plate. They are always attracted to the negatively charged plate. Thus, the drop must have a positive charge, for opposite charges attract each other. A good question now would be, how does the drop become charged? The water in which the bubble breaks carries no charge, so it looks to us like the drop becomes charged at the moment it breaks away from the jet. But just how this happens is not yet certain. I have measured the positive charge on these drops from bubbles of many different sizes, and we are presently trying to see just how significant this may be in putting positive electricity into the atmosphere. Now, included in all of this is arguing and debating with my fellow scientists. There are some who think that this may be of relatively minor significance, but we're just going to have to do a lot more work on these particular effects before we can settle that question. Now, Now, at this time, I'd like to turn to another phenomenon, which I think is very exciting and of significance in putting positive charge into the atmosphere. And this has to do with the eruption of volcanoes in the sea. Now, I realize in this day and age, one doesn't expect to find many volcanoes erupting in the sea. But when and if one does erupt, it is of interest to us to find out if any electrical effects are being produced. Now, how does one go about simulating a volcano in the laboratory? It would certainly be easier for us if we could do that. Well, there is a way. This may not look like a volcano, but we have all of the necessary ingredients. We have the lava, we have seawater, and in a few seconds, we'll have some heat. Now it's hot enough, and I'll let some seawater fall on the hot lava. The seawater sizzles and explodes into a cloud of salt particles and water droplets. Here it is in slow motion. By studying slow motion films, we hope to learn something more about how the cloud is formed. And now let's find out if our artificial volcanic cloud carries any electricity. And to do that, we will use this probe from this electrometer. And now we'll turn the electrometer on and center the needle at about 0 center. And when the cloud comes up and goes by the probe, if you see a motion of the needle to the right, it indicates that the cloud carries a positive charge. If you see a motion of the needle to the left, it indicates that the cloud carries a negative charge. Let's reheat the lava, and we'll see what happens. It moves to the right, indicating a positive charge. The cloud carries positive electricity, just like the jet drops. On the basis of these experiments, it would seem plausible that the clouds that rise from volcanoes where the lava makes contact with the sea will carry positive charge. Clouds which carry enough electric charge, positive or negative, often produce lightning. In November 1963, about a year after I did the volcano experiment in the lab, a real volcano burst through the surface of the sea about 20 miles south of Iceland. An expedition was formed to observe it. These are some of the films we took. Seawater appeared to be flowing into one side of the crater during this part of the eruption. Charles Moore put instruments on the small boat that we used and found that these clouds were very highly charged with positive electricity. If you watch carefully now, you will see a lightning stroke. Let's look at that frame. I think you will agree with me that the volcano clouds were highly electrified. Here are some time-lapse pictures taken at night. The flashes of light are lightning. This was photographed by Dr. Bernard Vonnegut. Now, does all this prove that the positive charge found in the clouds above volcanoes that rise through the sea originates when seawater strikes hot lava? It certainly does not. There may be, in fact, there probably are, many other electrical effects going on. We are just beginning to find out about them. In this film, I hope I have been able to show you that we must look to the surface of the sea to find the true beginnings of some of the processes that we believe influence weather. Some of the things I have said, especially those regarding the production of charged particles by the sea, are yet very speculative. And on this subject, there are some scientists who would disagree with me. But I want you to understand that this is the way we work. By continually questioning each other and by asking questions of nature in the way of experiment, we slowly get at an understanding of the way things work. We have gone into several areas of research in our discussions: chemistry, physics, oceanography, and even volcanology. But much more work remains to be done before we have a complete understanding of the relation between the formation of rain and sea salt particles and the electric charges which originate at the surface of the sea.